Soil erosion and erosion. So soil is one of the most fundamental and basic resources. Although variously dubbed as dirt, sometimes as something of insignificant value, but you cannot survive without soil. It's the basis to history. It is a non-renewable source. Over the human time scale, it can take about 100 years to form only 5 cm of soil. So, meaning the productive land are finite and comprise only about 10% of the land area, yet it can supply for a billion people. So this is why we manage the soil and why we learn how to prevent soil erosion, what causes soil erosion, how to calculate the soil erosion. The goal of soil management is to further enhance the functionality of soil to meet the ever-increasing food demand, filter air, purify water, and store carbon, among others. Is table 1.1, the function of soil from food security to the production of biofuel. So a lot of function. So, so soil management, it is estimated that the world population will reach 9.5 million by 2050. The rate of increase is country specific, with most of the increase in developing countries. Estimate indicate that the current growth rate is about 78 million people per year. So this rapid increase in population, meaning that the requirement for food, water, clean water, energy, and basic necessity will increase accordingly. So at the moment, it's April, the world population is 8.3 billion. The population growth will result in increased demand for food, which will put more pressure on soil and water resources, leading to increased soil degradation. So our challenge is to balance food production with soil and environmental quality. Since land is a finite source, the same piece of land will require increased input to produce more food, which increases risk for environmental pollution. Okay, just a side. So agent that degrade soil. So this is some of the agent that degrade the soil, but in the book there are more. We have water erosion, wind erosion, tillage erosion, soil compaction, drainage. So continue in the book, nutrient depletion, salinization, uh, solidification, acidification, biological degradation. So wind, water and wind erosion are the leading agent of soil degradation. So soil compaction, poor drainage, nutrient depletion, acidification, solidification, and all the until biological degradation. This process degrades the soil under specific condition due to management material from human, climate, terrain, and water. So the major erosion is coming from wind and tide. Geologic and accelerated erosion. Geologic erosion is defined as the normal process of weathering that generally occurs at low rates in all soil as part of the natural soil forming process. The rate of geologic erosion varies with soil parametering, climate, and others, but the estimated rate is around 1 megagram per hectare per year. The other one is the accelerated erosion. So the soil erosion become a major concern when the rate of erosion exceeds a certain threshold known as the accelerated erosion. So geologic erosion is the natural soil forming process. The one is accelerated erosion. So this accelerated erosion is due to anthropogenic causes or human doing, like intensive plowing, yes, uncontrolled grazing, biomass burning, deforestation, and many more. Water erosion. So on a global scale, water erosion is the most severe and extensive type of soil erosion. The land affected by water erosion represent about 50% of the total degraded land, while wind erosion affect about 30% the total degraded land area. So runoff washes away soil particles from sloping and bare land, while wind blows away loose and detached soil particles from flat and unprotected land. But soil erosion normally occurs in desert area, arid, indeed. So water erosion is the dominant form of erosion in humid, subhumid, and semi-arid region characterized by frequent rainstorm, but also can occur in arid region due to intense storm, like in African continent. They seldom receive rain, but once it's rain, it's intense rain. One of the most severe uh, type of water erosion is the concentrated gully erosion, so which can cause severe soil erosion even in a single event of high rainfall intensity. Example of uh, concentrated gully erosion. So the excessive gully erosion can wash out crop, expose the plant root, and lower the groundwater table. So gullying is the major source of sediment and nutrient loss, which also cause drastic alteration in landscape aesthetic and remove vast amount of sediment. So another one is the wind erosion. So wind erosion is widespread phenomenon. So most of the material carried by wind consists of a seed-sized particle, and the deposition of this material, there's a term for it, low, lows, lowest, has developed into very fertile and deep soil. The thickness of most lowest deposit range from 20 to 30 meter, can be as thick as 335 meter. That one is the contoh di Loess Plateau in China. So the rate of wind erosion, it's increased in the order of arid. So what is arid? It's a region with severe lack of water. So in quantity, this area receive around 250 millimeter or 10 inches of rainfall only per year. Yes. So from arid to semi-arid, dry, subhumid, and the humid area, our Malaysia is a humid area. So unlike water, wind has the ability to move soil path up and down the slope and can pollute both air and water. While arid land are more prone to wind erosion than humid ecosystem, any cultivated soil that is seasonally disturbed can subject to wind erosion, particularly in windy environment. So how does wind causes water pollution? Because it said here can both pollute air and water. So wind erosion has intensified in recent years due to frequent drought and the expansion of agriculture to marginal land. So wind erosion, it carries nutrient like nitrogen, phosphate. So this nutrient that contribute to the water pollution. So the consequence of soil erosion, the accelerated soil erosion causes adverse agronomic, ecologic, environmental, and economic effect both on site and the off-site. It not only affect the agricultural land, but also the quality of the forest land, pasture land, and range land. Even during the growing season, row crops are susceptible to soil erosion. The on-site consequence involve primarily the reduction in soil productivity, while the off-site consequence are mostly due to the sediment and the chemical that transported away from the source into natural water by stream and deposition, depositional site by wind. Okay. So the on-site is the, let's say, the farm itself. So when the erosion occurs, like normally wind and water, so all the soil, the topsoil, pesticide, fertilizer got washed away from the farm into the nearby river, water source, or stream. So that is the on-site and off-site consequence. So the on-site consequence, the primary on-site effect of erosion is the reduction of the topsoil thickness. What is the importance of the topsoil? Which result in soil structure degradation, soil compaction, nutrient depletion, loss of soil organic matter, or many new seedling emergence, reduced crop yield. So that is the effect of topsoil thickness reduction. So meaning the topsoil is essentially, we can say, it's the skin of the earth that support the life. So in the topsoil, this is where the microorganism and the organic matter stay. Yes. So any erosion that remove the topsoil will result in this effect. But one may argue that according to the law of conservation of matter, yes, correct, soil loss by erosion in one place, meaning the farm, are compensated by the gain at the other place. The problem is that, yes, that one is correct. We didn't lose the fertilizer or the topsoil, but it's moved to something, a new area. But the problem is the eroded soil or the topsoil is often deposited in condition that no crop can be grown, like the water stream. How can you plant uh, a, a food there, vegetable there, for example? That's why the control and management of soil erosion are important, because when the fertile topsoil is eroded away, the remaining soil is less productive with the same level of input. The other one is the offsite consequence. So water and wind uh, erosion preferentially remove the soil layer where most agricultural chemical like fertilizer and pesticide are concentrated. Thus, the off-site transport of sediment and chemical causes pollution, sedimentation, and silting of water resources. Sediment transported off-site alters landscape characteristics, reduce the wildlife habitat, and cause economic loss. This is example of the off-site consequence. So this is the, you can say this is the fertile land, but due to the erosion of water, maybe some wind, there's no cover at all. So the topsoil is sedimented on the in the water stream. So a number of changes in soil physical, chemical, and biological process occur due to accelerated soil erosion. So what is accelerated soil erosion? When the erosion occurs above certain threshold, so we call that accelerated soil erosion. So this process rarely occurs individually, but in tandem with one another. For example, a compacted soil are more prone to soil structural deterioration. This one is the physical process. You can also look at table 1.2, page 9 in the book. Salinization, that one is the chemical process. This is due to the compacted soil and reduced microbial activity. This is under biological process. Then when we compare to the non-compacted soil, so some processes are more dominant in one soil than in another. For example, salinization is often more severe in irrigated land with poor internal drainage than in well-drained soil of favorable structure. Then the one is this slide is you can refer to table 1.2, implication of increased soil erosion on soil processes, properties, and productivity. For example, refer to the book, page 9. For example, chemical process. So increase in acidification, salinization. So all of this term can refer to the book. It's available. Page 16. Yes, page 16. 16. And 1.5.5. So increase in acidification, salinization, solidification will decrease the cation exchange capacity of the soil. This is about the soil, nutrient storage and cycling of the soil, and biogeochemical cycle of the soil. But what caused the soil erosion? Yes, anthropogenic, one of it. So anthropogenic activities involving intensive cultivation, urbanization, deforestation, or many things. Even the cultivation at steep slope can also risk accelerated soil erosion, which is true. Normally we see this black pepper farm. They normally use the slope area to plant the black pepper. To table 1.3, page 10. Soil erosion causes and associated environmental and societal issue. Concentrated pasturing of cattle and sheep herd on the same piece of land for too long in low livestock farm can lead to repeated trampling, soil displacement during traffic, and overgrazing. Soil compaction is also one of the effect with the concentrated pasturing of cattle and sheep, because the trampling by the cattle causes soil compaction, reduce root proliferation and growth, and decreases water infiltration rate and drainage. What else? Deforestation. So how does deforestation cause soil erosion? So deforestation, it removes the vegetative cover and accelerated soil erosion, which accelerate the soil erosion. So the forest not only provide essential ecosystems such as soil erosion control. So we have tree, very high tree. So what does the tree do? So when it's rain, the rain coming from the sky, from the cloud, without the tree, will impact that one is later. So how the mechanism of soil erosion. So that droplet of rain is slowed down by the leaf from the tall tree. And then it's flowing down again. And normally in forest, we have this vegetative cover. So what does it do? It prevent the raindrop to directly impact the soil. So that's why that's how forests can prevent or minimize or act as a soil erosion control. So since we discussing soil erosion, so how much soil loss is acceptable? So while soil erosion cannot be completely curtailed, excessive erosion must be reduced to a manageable or tolerable level to minimize adverse effect on soil productivity. The magnitude and impacts of soil erosion on productivity depend on soil profile and horizonation, terrain, soil management, and climate characteristic. So in US, the estimated average tolerant level of soil erosion in soil and water conservation planning is about 11 megagram. But this tolerant value is varies among the soil with range from 2.2 to 11 megagram per hectare per year. So in ton, 1 megagram is equal to 1,000 kilogram or 1 ton. So 11 megagram is around 11 ton of soil erosion. Tolerable. How about Malaysia is depend on the soil erosion class. Refer to table E3. So very low is less than 10 ton per hectare per year. So which is similar to the estimated average tolerance in US. So tillage, erosion, and soil loss due to crop harvesting. So erosion by wind and water has traditionally been recognized as the only major component of total erosion. Now, it's tillage erosion and erosion due to root crop harvesting. Like the picture, this is a carrot. So when you remove the carrot, you don't just remove the carrot, it will track along the soil. The tillage erosion refers to the gradual translocation of soil down the slope downslope due to frequent and intensive tillage operation. This is particularly tillage is referred to the up and down slope plowing, like this picture. Can move soil downhill and accumulated eroded soil at the bottom of the cropland. So tillage erosion depend on tillage tool. So chisel plowing can move soil near the soil surface, while wallboard plowing can move soil for the whole tillage depth. So how about the uh, root crop harvesting? So the large amount of soil attached to the root can be removed with the harvest of root crop, including sugar beet, carrot, potato, sweet potato, yam, cassava, and many others root crop uh, harvesting. But in places where no adequate equipment for sorting and washing the root crop, the loss of soil due to crop harvesting can be as much as the 20% of the total soil loss and can be as high as 22 megagram, which is 22 ton per hectare per harvest. So this rate of soil loss due to crop harvesting can be equal or higher than the water and wind erosion. So it's a concern, the root crop harvesting. The implication of soil loss due to root crop harvesting to total erosion and nutrient losses deserve consideration. So combined effect of water, wind, and tillage erosion along with the soil losses due to root crop harvesting can cause a threat to sustainable agriculture. The next is the soil compaction. So another major soil degradation is the soil compaction. So the word compaction meaning the soil is compacted due to some heavy thing. In this case, the heavy farm equipment and animal traffic, like trampling by the cattle or concentrated cattle herding. The weight and size of field equipment, like tractor harvester, is very big, have gradually increased since the mid 1900. So in 2010, one tractor can weigh as much as 20 to 45 megagram or ton. The one is 2010. Now they should be more with the technologies. The repeated wheel traffic during the tillage, the planting, harvesting, manuring, and weed pest control degrade the soil structure and causes surface and subsurface compaction in cultivated soil. Subsurface compaction or compaction just below the depth of tillage occurs when a compacted subsurface horizon of higher bulk density and lower total velocity than the topsoil known as the flow pan is formed. Okay. The need for soil and water management. So managing soil is not only about adding the right amount of fertilizer and water to soil, but it is also about enhancing the resilience or capacity of the soil to buffer or resist changes. A well-managed soil should be able to provide nutrient when soil fertility is low. It can retain water during the dry period. This is a well-managed soil and release water during the wet period. So the goal of soil management is to manage and conserve soil fertility to enhance its performance for a sustainable agricultural production. So a well-managed soil should allow profitable farming while maintaining or improving the. So it happened at the same time, maintaining and improving the environmental quality. So water erosion, this one referred to slide, uh, sorry, chapter 2. Step book, soil conservation and management. So, so chapter 2 is focusing on the water erosion, just water erosion. So water erosion is the wearing away of the soil surface by water from rain runoff, snowmelt, and irrigation. So rainwater driver of the water erosion in the form of runoff. So rut is runoff, refer to the movement of water on the soil surface by gravity. So it's when it rain, it moves across the land. So that uh, movement of water, we call it a runoff. It carries, so once it's moved on the surface of the soil, it will carry the soil organic and inorganic particle and deposit them over. The eroded material can either form a new soil or simply fill the stream, lake, and reservoir. So water erosion occurs in all soil to varying degrees. Slight erosion is actually beneficial to the formation of soil, but severe or accelerated soil erosion will affect the soil and environment. So what is accelerated soil erosion? So when the soil loss is above the tolerable soil loss level. Okay. Type of water erosion. The main type of splash, rail, gully, stream bank, and tunnel erosion. So sheet and splash erosion are sometimes known as the interrail erosion. Note that the different type of erosion are interconnected. For example, splash erosion is the precursor of interrail and gully erosion. So splash erosion, this is as when the raindrop falling on the soil surface without the vegetative cover. So raindrop falling on soil surface disperse and splash the soil, hence its name. So it displaces the particle from their original position. Splash erosion is caused by the bombardment of the soil surface by impacting raindrop. So the process of splash erosion involves raindrop impact, splash of impacting raindrop. The process of splash erosion involves raindrop impact. Okay, the diameter of the crater can be as large as 10 centimeter in diameter, which is quite big. Raindrop striking the soil surface develop a raindrop soil particle momentum before releasing the energy in the form of splash. So these raindrops strike the soil like a small bomb, forming crater or cavity of contrasting shape and sizes. The soil displacement by splash erosion can be as high as 1.5 meter and exceed 5 meter in horizontal distance under windy condition. Okay. Further is soil displacement by the splash erosion. Then we have interreel erosion. As soon as the runoff starts, so what is runoff? Water, movement of water assist by the gravity. So as soon as the runoff start, a reel or small channel will develop, which is true. The portion of runoff that flow between reel can cause sheet or interreel erosion. So it start with reel, then it will widen into the interreel erosion. So this type of erosion is mostly due to shallow flow. Some particles are carried away in the runoff flowing in a thin sheet, and some particles concentrate in small reel. Interreel is the most common type of erosion. Splash interreel erosion make up about 70% of total soil erosion and occur simultaneously. Although splash erosion dominate during the initial process, during the raining year, during the rain, splash erosion will dominate. After that, reel will form due to the runoff. So that reel will combine, become the interreel. So interreel erosion is a function of particle detachment, rainfall intensity, slope gradient, and slope length. We have some equation here. So we have this calculation example. So equation 2.1. So DI is referred to interreel erosion rate. Ki is the rate of interreel erodibility. R is the runoff rate. I is rainfall intensity. SF is slope factor. L is the slope length. The slope factor is equal to SF 2.05. Okay. So this SF is calculated by this equation, where theta is the slope angle. Okay, this is real and interreel erosion. So real erosion, the term real erosion refer to the soil erosion that occurs in small channel or ring. So real erosion occurs due to concentrated rather than shallow flow. Runoff water that concentrate in small channel erode soil faster than interreel erosion. The force of flow and soil particle creeping along the reel bed enlarge the reel. So this is the second most common pathway of soil erosion. So the real are easily obliterated by tillage erosion, but can cause large quantity of soil loss, especially under intensive rain. So real erosion is a function of soil erodibility, runoff transport capacity, and hydraulic shear of water flow. So soil erosion occurs mostly through the simultaneous action of inter-reel and reel erosion in accord with the steady state sediment equation. So delta QS delta X equal to dt plus di, where QS is the sediment delivery rate in reel, X is the length of the reel. So the symbol here delta is referred to the rate. So, so meaning the sediment delivery rate is dynamic, it changes with time. Uh, Same as the length of the reel. Dia berubah ikut masa. That's why they put delta there. So I write this integration to show the limits from when to where, from when to when. Then gully erosion. Gully erosion is the soil movement along channel or drainage line due to concentrated runoff. It's either V or U-shaped channel. The incision channel of at least 0.3 meter width and 0.3 meter depth. Gullies are larger channel than reel, which are responsible for reel erosion. There are two types of gullies, ephemeral and permanent gullies. So the ephemeral gullies are shallow channel that can be corrected by routine tillage operation. In contrast, the permanent gullies are too large to be smoothed by the regular tillage and caused by machinery traffic, requiring expensive measure of reclamation and control. So ephemeral gullies following a removal tend to form in the same point of the field if not controlled. Even if gullies are repaired by tillage, soil is already lost due to the off-site transport of the eroded material. So the permanent gullies is what I showed you previously. This is the, we can say this is the permanent gullies. Because ephemeral gullies, that one can be corrected by a routine tillage, but this one is quite large. It's require reclamation, then reclamation. Wait. Process of water erosion. So there are four steps of water erosion, which involve the detachment, transport, redistribution, and deposition of soil particle. The process of soil erosion act in sequence table 2.1. This is page 29. So the process of water erosion begin with the discrete raindrop impacting the soil, which is the splash erosion. Then detaching of soil particle and finally transporting soil particle downstream. Detachment of soil release fine soil particle which form the surface seal. The seal plug the open-ended and water conducting soil pores, reducing the water infiltration and causing the runoff. At the micro scale level, a large raindrop initiates the whole process of erosion by weakening and dislodging an aggregate, which eventually lead to large-scale soil erosion under the intense rainstorm. So refer to table 2.1. Okay. It starts with the detachment. Then transport and redistribution, like the selective removal modify the texture and structural properties of the original soil. This is a role of water erosion. Then last is the deposition. Placing the deposited material back to its origin can be costly. So four step of water erosion. So how to measure the erosion? So knowing the amount of soil leaving a field is essentially assess the magnitude of severity of erosion. A certain effect of erosion on soil productivity and water pollution. Understand and manage sedimentation in depositional areas. Designing and establish erosion control practices. And develop mathematical model and test their applicability for soil erosion prediction. So measuring the soil erosion require the consideration of plot size and knowledge of factor that affect data variability. So choice of the plot size proper replication way to minimize measurement variability. Type of version plot include micro, medium, and universal soil loss equation plots. Large plot or field scale or watershed. The amount of soil loss per unit area varies depending on the plot size because larger plot capture interreal and possibly ephemeral gully erosion. They are preferable over micro plot to characterize the soil erosion. So we have these three type. Start with micro plot, medium or USLE plot, and the large plot or watershed. So each have its own function. Example, microplot, the size is vary from 0.05 to about 2 meters square. So this microplot are frequently used to provide hands-on opportunity to manipulate and understand the principle of soil erosion process and factor under simulated rainfall. Then medium or SLE plot. So this medium size plot often similar to that standard plot, which is for multiply with 22.1, 4 times 22.1 meters dimension, used for the evaluation of the USLE model. Then the large plot, around 100 meter square. So large plot is to study the real and interreal erosion and ephemeral gully erosion for long-term study. Agent of erosion, agent of water erosion. Two main agents affecting water erosion is the rainfall and the runoff erosivity. So rainfall erosivity, this is calculating the how much year datang, yeah, it is how does it influence the soil erosion. So rainfall erosivity refer to the intrinsic capacity of rainfall to cause soil erosion. Water erosion would not occur if all rain are non-erosive. So since this is hardly the case, knowledge of rainfall erosivity is essential to understand erosional processes, estimating soil erosion rate, design erosion control practices. Properties affecting erosivity are amount, intensity, terminal velocity, drop size. This is talking about the rainfall erosivity and drop size distribution. So you can refer to the table 2.3, page 38. So start with the amount. So more rain mean more erosion. Next is the intensity. Intensity is the amount of rain per unit of time. Intensity is normally less than 70 mm, but can be as high as 150 mm per hour. Still, you can recall for the arid region for a year, 110 mm. Intensity is correlated with erosion. And another factor is terminal velocity, meaning the raindrop. The, the velocity of the raindrop before it impact the soil, before it reach the soil. So that what we call the terminal velocity. So the terminal velocity can be as high as very fast, quick 35 kilometer per hour, which can displace soil as far as 2 meters, or if you refer back to the previous discussion, up to 5 meters width in a windy condition. So terminal velocity increases with the increase in raindrop size. Raindrop of 5 mm in diameter have a terminal velocity of 9 meters per second. Another last one is the drop size. So raindrop diameter ranges from 0.25 and 8 millimeter. In intense storm, raindrop can be as large as 8 millimeter. While raindrop size increases with rain intensity, it may decrease when intensity exceeds 100 millimeter per hour. So how do you measure the raindrop? So refer to table 220, this one. So the drop stain use of high absorbent paper with water soluble dye and flour pellet, collecting and drying drop in a container with flour. The method used to measuring raindrop size distribution. The rain intensity. So a combination of a high amount of rain with a high intensity produces high erosion. So intense storm are of short duration, but can cause a large amount of erosion. The total storm intensity is made up of the intensity of the individual raindrop. The energy of the raindrop due to its motion is also known as the kinetic energy, represented by equation 2.6. The kinetic energy E equal to 1 over 2 mv square. M is referred to the mass of the falling raindrop in gram, and v is the velocity of the fall, refer to the raindrop in centimeter per second. And we have this universal soil loss equation, USLE. So USLE and the revised USLE use, for example, data on the electricity to compute E, and then compute the total kinetic energy of the storm. So when rainfall is measured in daily total, the E in USLE is estimated as a function of rainfall depth. And intensity I. So intensity is the amount of rain per unit time, referred to table 2.3. So E equal to, okay, the equation 2.7. Next is the runoff erosivity. The previous day we discussed the rainfall erosivity. Now is the runoff erosivity. So agent of water erosion, the two main agent is rainfall erosivity. Another one is the runoff. erosivity. So for the runoff erosivity is the ability of runoff to cause soil erosion. Raindrop impacting soil surface loosen, detach and splash soil particle. One runoff primarily carries soil particle. Interaction among rain, runoff and soil particle result in erosion. Floating and tripping soil particle in turbulent runoff also contribute to aggregate detachment. Rain has more erosive power than runoff. The kinetic energy of the rain of mass equal to m and terminal velocity v equal to 8 meter per second is this equation. The calculation here is to show that mm, that the rain has more erosive power than the runoff. Let's say using the equation 2.1 with terminal velocity of 8 meter per second for the rainfall, so we have 32 uh, kinetic energy, 32 m. Assuming that 25% of the rain become runoff, because some rain they get absorbed into the soil, but some yes can become the runoff. So assuming 25% of the rain become runoff, with the runoff velocity is 1 meter per second, because this just assist by gravity. Then E is equal to 1 over 8m. You see the difference? So that's the E kinetic energy of the rain is 256 times greater than that of the runoff. So if 50% of the rain had become runoff, the E would be greater than 128 times. But even say all the rain become runoff because due to the soil compaction, it E for the rainfall still greater than the runoff erosivity. So early erosion models such as USLE considered only rainfall erosivity, but the improved model include both rainfall erosivity and runoff erosivity, providing a more accurate estimation. For example, the modified USLE or MUSLE incorporate runoff erosivity as RE equal to equation 210, 2.1, 2.10, where RE is the rainfall runoff erosivity, both EI30 is a product of rain E, and its 30-minute intensity I30 of the USLE megajoule millimeter per hectare per hour. Alpha is a coefficient, QD is the runoff depth mm, while Q is the peak runoff rate millimeter per hour. Later we will example how to apply this equation to calculate the erosivity. So estimation of runoff. Okay. Determining the maximum runoff rate and total amount of runoff leaving a watershed is of great utility to design and construct mechanical structure of erosion control, design and establish conservation buffer, estimate the amount of sediment and chemicals lost in runoff, convey runoff water safely in channel or grass waterway at a reduced safe power. So determining rate and volume of runoff involve the consideration of various runoff factors such as topography, soil surface condition, soil texture, water infiltration, vegetative cover. All of this is available later in table 2.5 or table 2.5 and table 2.4. So time of concentration. This is the time required by the runoff water to travel from the farthest point in terms of the travel time to the outlet of the watershed. Assume that the rainfall only at the lower end of the watershed, such being the case, runoff water from a point near the upper end of the wetted portion would reach the outlet of the watershed in a shorter time than that from the most distant point of the watershed if it ran in the whole watershed. So time of concentration later we will calculate this is the time required for the runoff water to travel from the farthest point in terms of the travel time to the outlet of the watershed. So the time of concentration uh, depend on the flowing factor, the surface roughness, watershed slope, size of the watershed length, and shape of the channel. So surface roughness, the smoother the surface of the watershed, the shorter the concentration time. So the growing vegetation, residues, rock outcrop, ridges, depression, and other obstacles retard the overland flow. Thus, water travel time in a vegetated watershed increases unless the flow is conveyed in constructed channel. And the surface roughness expressed in terms of Manning roughness coefficient. This is referred to table 2.4, the table. So based on the condition of the soil surface, for example, bare soil, so the roughness is 0.011. We have the watershed slope. The steeper the surface of a watershed, the shorter the time it takes for water to reach the outlet. So a watershed is also known as drainage basin or catchment. So terracing and the establishment of conservation buffer reduce the watershed slope and thereby increase the travel time of water flow. So in urban areas, grading changes the slope. Channel with reduced roughness increase runoff velocity and peak discharge. Establishment of pond reduction of soil slope increase the time of concentration. Next is the size of the watershed. So the larger the watershed, the greater the contributing area to runoff, but the longer the time for runoff to travel, which is true. So this is the size of the watershed referred to figure 2.6. So a large watershed under both overland and channel flow A and two watershed B and C of the same size but oriented differently, yielding thus different time of concentration. So size, shape, orientation of the watershed affect runoff travel time, peak runoff rate with TCV or time of concentration. For overland flow and TCH is the time of concentration for channel flow. This is for size of the shape. This is for the length and shape of the channel. The water flow from the farthest point in flow time under field condition is not always laminar. But tend to flow in different way, including through shallow rills, open channel as concentrated flow, and three is the diffuse interrill flow. After a shorter distance, interrill or sheet flow become concentrated flow in channels. The smoother the channel, the shorter the time reach travel time to reach the outlet. Sloping and stretch channel accelerate the runoff velocity. The straightened channel increase runoff velocity as compared to the meandering and tortuous channel. So the time of concentration is computed as Tc equal to equation 2.11. Tc is time of concentration in minute. L is the maximum length of flow in meter. S is the watershed slope, meter per meter. Rainfall later we see what does it mean by meter per meter of the watershed slope. Because what slope normally the unit is theta angle. Rainfall duration can be higher, lower, or equal to the time of concentration. So the time of concentration for overland and channel flow is the sum of both type of flow as question 2.12 there, TCV, TCH. TCV is the time of concentration for overland, TCH is the time of concentration for channel flow. So TCH, TCV have their own equation. So TCV equation 2.13, TCH 2.14, L is slope length of the watershed in meter, N is the meaning roughness coefficient, the one referred to table 2.4. S is the average slope gradient of watershed meter per meter. LCH is the channel length from the farthest point in flow time, the one in kilometer. NCH is the roughness coefficient for the channel. A is the area of the watershed. SCH is the slope of the channel, meter per meter. So in topographically complex watershed with a large network of channels, the concentration is estimated for each segment in the watershed as Tc equal to Tc1 until Tcn. So for a complex watershed, meaning there's a many overland, there's a channel flow. So to calculate the time of concentration, you need to add up all sum or total all the TC. So where TC1 until TCN are the time of concentration for watershed segment 1, 2, and N is the total of flow segment. Let's see example 1. Estimate the time of concentration for a watershed of 1.5 kilometer that has an overland slope length of 80 meter with a slope gradient of 5.5%. The channel length is 6 kilometer with a slope of 0.9%. The remaining coefficient of roughness for the watershed is 0.5. And that for the channel is 0.014. So refer to equation 2.13. So L refer to the slope length 80 meter. N refer to the roughness, meaning coefficient of roughness for the watershed when 0.15 divided by 18. S is the average slope gradient, in this case in percentage. So 18, so 5.5 divided by 100 to get the value 0.055. Then TCV, time of concentration for the overland, is around 0.59 589 hours. For the channel, so LCH refer to the channel length 6 kilometer, NCH is the meaning 0.014. A is the watershed area 1.5 kilometer square, and S is the slope for the channel is 0.009. So TCH is 0.839 hours. So the time of function for both type of flow, this is what example of complex watershed with different type of channel and overlane flow. You need to add it up. So the total TC is 1.428 hours. Runoff volume, the total amount of runoff leaving a field can be computed using the runoff curve number or CN as follow. So QD is the depth of runoff. In mm, the R day is the amount of rainfall for that day. In millimeter, IA is the initial abstraction that account for the surface water storage in depression or ponding. So IA you need to calculate using equation 2.18. So S is the retention meter in mm. So substituting 2.18, the IA into equation 218 to 18 to 217, you get 219. Just replace the IA to 0.2 S. S is retention parameter. Does S become the parameter that account for the difference in soil surface condition, land use and management? So S here refer to 25,400 divided by CN. CN is the runoff curve number minus 254. So S in this runoff volume is not the slope gradient. Just see in time of concentration, S is referred to a slope, but in runoff volume equation here, S is referred to the retention parameter, can be calculated by equation 2.2. Among factors that influence the curve number, runoff curve number, CN, are the hydrologic soil group, land use, soil management, cropping system, conservation practice, and antecedent water content. So the value of CN vary from 0 to 100 depending on the soil and surface condition. This is referred to table 2.5, page 45, long table. Oh, this is table 2.5. If you refer to this table, over here is a hydrologic soil group A, B, C, D. Each letter have their own condition for the soil. All right. So A, hydrologic group A. So this soil, this is the characteristic of the soil. Normally it is the description given in the text in the question. You need to identify from this A, B, C, and D, this group. So A refer to soil that are deep, highly permeable. Their textural class include sand, loamy sand, and sandy loam. Because of the low clay content, soil in this group have very high saturated hydraulic conductivity and infiltration rate, even when completely wet, and thus have the lowest runoff potential. Deep loess and sandy soil are part of this group. So loess is referred to the soil that is transported by the wind, or a product of wind erosion. B, this group includes silt, loam, and loamy soil uh, which are moderately deep and permeable. They transmit water at a slightly lower rate than group A, although the rates are still above the average values. The moderate permeability result in soil with moderately low runoff potential. See, these soil are less permeable, shallower than those in group B because of relatively high clay content or the presence of slowly permeable layers below the topsoil. Sandy clay loam are within this group. This soil have moderately high runoff potential due to the low rates of water transmission. This group comprises clay, loam, silt clay, sandy clay. Okay, this is very low water infiltration. So based on the group here, it is actually categorized as how the water can infiltrate through the soil. A is the, you can say, the fastest, the best. D is the slowest. All right. Example 2. Estimate the runoff amount that is produced by a watershed of 2 kilometers square, receiving an average precipitation of 50 millimeter per day. The watershed is under three different uses. Half of the watershed consists of agricultural land, with crops planted in straight row under good condition. A third of the watershed consists of residential area, with 30% of impervious surface from houses and paved driveway, and the rest of the watershed is underwood, with dense little cover. The soil are part of the hydrologic group B. So, solution. So impervious area, pervious area, this is referred to the urban area. So the information is available in the example, the question. So 30%, you see, of the impervious surface from houses and driveway, and the rest of the watershed is underwood. So that only 30%. So impervious refer to the roof, the street, parking lot, driveway. That is the impervious area. Pervious area is, this is talking about urban area. Pervious area refer to the lawn, the park, the golf courses. So impervious area, the value 98 and 61 here. You can refer to table 2.5. So impervious, pervious. So 98 hydrologic group B stated in the example question. So B for the impervious area, the value, or is it the CN is 98, and CN for pervious area is 61. But not all of the runoff curve number refer to impervious area, only 0.3%. So another 0.7 is the pervious area. So that's why you need to calculate. That's why they calculate impervious area instead of 98 is 29.4. Pervious area is 42.7. Next is the table. So land use row crop in good condition, residential area, the woods. So the residential area, the fraction based on the question is half. No, half. A third. A third means 1/3. Yeah? A third of the watershed consists of residential area. So within the residential area, what the third of the fraction, meaning in that watershed, 2 kilometers square of watershed, one third of it is the residential area. Within the residential area itself, there are two types, impervious and the pervious. So for residential area, the weighted CN number, CN is 24. Meanwhile, for another one is a row crop in good condition. So row crop also available in the question. Half of the watershed, the question is in page 46. Half of the watershed consists of agricultural land with crops planted in straight row under good condition. So 0.5, 50% row crop in good condition. Then you need to identify the CN. So under row crop, this row, straight row, and it said the crop is in good condition, good. So under hydrologic soil group B, the value is 78, but only half of the fraction of the area, the watershed area. So the weighted CN is 39. The last one is wood. So for the wood is a watershed is underwood with dense litter cover. Mm, so the rest of it, so the fraction of this, if you add it up, is equal to 1, refer to the 2 kilometer square of the watershed. So once you identify the fraction, then find the average curve number CN for the wood. So since this is a dense litter cover, which is the ungrassed, the value is 55. So weighted curve number 92, the total CN is 72.2. So calculate the retention parameter S. This is not talking about S the slope. This is S the retention parameter. So we have 97.8 millimeter. Equation 2.2. This is equation 2.2. This is equation 290. So from the value of S, we can calculate QD, which is referred to depth of the runoff. So QD equal to 7.2 millimeter. So are they refer to amount of rainfall for the day? In this case, it is available in the question. Average precipitation of 50 millimeter per day. So the runoff in term of volume is computed as QV, 2 kilometer square, which is the watershed area, multiply with, this is the unit conversion, and this is the QD. So QV is equal to 14.44 meter cube. All right. Next is the peak runoff rate. So the peak runoff rate, is the maximum rate of runoff that occurs during a rainfall event and is estimated by the rational and the modified rational method. The rational method is as follow. Equation 2.21. Q is the peak runoff rate. C is the amount of rainfall that become the runoff in a single event. I is the rainfall intensity. A is the area of the watershed. So 3.6 is the constant for unit conversion. The the modified rational method is expressed as Q equal to QD. So QD we know already, runoff depth, equal to alpha TC, which is the runoff fraction during the time of concentration. A is the watershed area in kilometer square. So replacing C equal to QD over R day, equation 2.23, and I equal to RTC over TC in equation 2.21 result in equation 2.25, where RTC is equal to alpha TC times R day. R day is the rainfall intensity or precipitation. Okay, so rearrange and give us Q equal to QD alpha TC times A divided by 3.6 times TC. That one is equation 2.27, where RTC is the amount of rain that fall during the time of concentration. On example 3, estimate the peak discharge rate for estimate the peak discharge rate for designing a runoff control system for a watershed of 2.95 hectare. If the intensity of rainfall with the 25-year return period for 10 minutes is 150 millimeter per hour, that one is the precipitation. Assume runoff coefficient equal to 0.95. So Q Q equal to CIA, C multiplied with A times I divided by 3.6. C is the amount of rainfall become the runoff in a single event. In this case, the runoff coefficient C is 0.95. I is the rain intensity divided by 2.6 multiplied with A is the uh, watershed area in kilometer square, not in hectare. Then Q which is the peak runoff rate, equal to 1.168 meter cube per second. One is example 4. Compute the peak runoff rate for example 2.2 using the modifier national method of 2 kilometer square watershed if the rainfall intensity is 50 millimeter fallen in 2 hours and time of consideration is 1.25 hours. So example 2.2. Page 46. So, okay, watershed area is similar to kilometers square. If the rainfall intensity is 50 mm, which is same, fallen in 2 hours, okay, then the time concentration is 1.25 computed. Peak runoff rate. So RTC equal to I. So RTC, this equation is equation 2.24. So I times TC. So in this case, I is 25 millimeter per hour because 50 mm fallen in 2 hours. So in the case of I, which is millimeter per hour, so you divide by 2. So 25 mm per hour multiply with 1.25 concentration of TC. So RTC is 31.25 mm. Then alpha TC equation 2.26. So RTC is 31.25. RD is 50 mm. That one is referred to example 2.2. So alpha TC or runoff fraction during the time of concentration is 0.625. Then using question 2.22, the modified rational method with QD available in example 2.2, alpha TC A divided by 3.6, then TC is 1.25. So the peak runoff rate is 1.99 meter cube per second. All right. We try this exercise plus 10 minutes. 10 minutes. For first, first two question. Let's see. So for the first, mm, for the question one, estimate the time of function for a 1.5 kilometer square watershed with soil hydrologic group C that has an overland slope length of 90 meter with a slope of 4.5%. The channel length is 4 kilometer with a slope of 0.7%. The remaining coefficient of roughness for the watershed is 0.17. And that for the channel is 1011. Okay. Example 2.2 ke 3.1. So example 2.1, 2.1, page 43. 2.1. All right, this example. So from this example, for the question, you can refer page 49 in the book. For time consideration for a 1.5 kilometers hydrologic group C that has an overland slope length of 90 meter with a slope of 4.5%. So you can now calculate uh, PCV. So L is referred to slope length of the watershed. So in the question, it's stated 90 meters. So here, instead of 80 is 90. N is referred to the meaning. So in this case, meaning for the overland TCV is 0.17 divided by 18. S is the slope gradient. So slope gradient for the overland is 0.045%. 0.45. So it's equal to apa? Jawapan apa? So 90 power of 0.6 multiply with 0.017 0.6 divided by 18 divided by 0.045 power of 0.3 0.72 hours TC CV. CV. How about the channel TCH? So for the channel 0.662. So for TCH, so 0.62 LCH is the length. So the length here is 4 kilometer. NCH refer to Manning. So in this case, Manning for this channel Equation 1 is 0.011 divided by AA is the watershed area. Watershed area 1.5 kilometers same. Multiply with the slope. The slope is apa slope? 0.7%. So 0.0007. No? So how much is this? 0.62. But so, 1 power of 0.75 right by 1.5 0.125 by 0.007. Yeah. 0.007 0.75. Okay, so TTH is 0.51. 0.51. So the answer for this question is TC, capital TC, the TC 0.51. 1.23 hours. That one is question 1. How about question 2? So question 2, that one is referred to example 2.2. Compute runoff depth and volume for problem 1. If an average precipitation of 50 mm per day fell in 2 hours period, a third of the watershed consists of agricultural land with crop planted in straight row with 50% under good condition and 50% under poor condition. A third of the watershed consists of residential area with 40% of impervious surface. The rest of the watershed is under grass and unburned wood with some little cover. Okay. So this is the continuity from the first question. If you see the soil hydrologic group C, now it makes sense, meaning you can refer to table 2.5 for the hydrologic group. So first of all, what to do? We calculate the impervious versus the pervious. In this case, it's 40%. 40% impervious, so 40%, 0.4 times 28, 29 point impervious. How about pervious? Is a 60.6, 61, 36.6. Next, you need to develop the table for the land use. So how about the crop here is you identify the fraction. Now average a third of the watershed consists of agricultural land with crop planted in straight row with 50% under good condition, 50% under poor condition. So meaning there are two value for CN here. It's both is straight row, which is equal to table 2.5. So for straight row, good condition is 78. Yeah. No, sorry, 85. Oh, so part. So for the impervious, 98, yes, correct. For the pervious is 74. So 0.6 times 74. Because this is hydrologic group C, 44.4. So for the straight row, it's how much? 88. So 88 straight. Good condition. 88 poor condition. It is under hydrologic group C. For poor condition is 85. Oh, the value. Oh, so good is 85. Poor is 88. But you cannot take the value as is because bagaimana? 50%. So a third, one third of the watershed consists of agricultural land. So one third meaning 0.33. So half of it is good condition. Half of it is poor condition. So can just half. Don't add up yet. So meaning for the straight row, you need to multiply with 0.5, huh? 0.5%. Huh? Okay, so 23 times 85 multiplied with 0.5 plus 88 times 0.5. So the first one, the first CN for the agriculture is agriculture CN. So 28.8. Next is the residential areas. In this case, a third is a residential area. So meaning 0.3 again. Residential CN equal to 39.2 times plus 34.4 of times 0.333, which is 27.8. Yeah. Okay. Acceleration area 37.8. The last one is mm, wood. So for wood, it's the rest of the watershed. So the rest is one third as well. Is undergrass and unburned wood. So undergrass, uh, undergrass. Okay, undergrass is less, and unburned wood is some little carbon. Mm, But not good. So 73, yeah, for the wood. So wood CN 73 0.333 times 73. Refer to hydrologic soil group C, ungrass but not burned 34.3. So this is a CN only. After you calculate CN, you need to calculate the S. So S equal to 25,400 divided by 28.8 plus 27.8 plus 24.2 minus 254. You get 59.16. 60 mm. That is S. Tension, tension, tension of water, mm. What else? The question one, you runoff depth. So runoff depth is QD. So QD equal to RD is 50. 50. Yes, 50. 50 per day. So 50, 50. Oh, straightforward then. 50 minus 0.2 times aquatic 60 pasal 2. Bagi dengan 50 plus 0.8 times 60 pasal 2. Oh, sikit eh. Oh, saya dah pasal 2. Oh, 15. 14.7 mm. Apa lagi? R. QV ya. QV equal to, still example 2.2. QV is apa size? 1.5 1000 dengan 15.7 divided by 1000. Berapa ini? 22.05 by Q cube. What's cube? So answer for question 2. QD is 14.7 millimeter. QV is 22.05 meter cube. Question 3. Compute the peak runoff problem for problem 1 and 2 using the modified rational method. So this is example 2.4. 2.4. Modify rational method. So modify rational method refer to equation 2.22. So first, identify the TC. So TC is 1.23 hours. So calculate RTC first. Then you calculate alpha TC. So RTC should to RTC equal to apa ya? 55 because 50 mm per day fall in 2 hour period. So I is intensity in an hour. So 25 times RTC 1.23 is to 30.75. That one is RTC in NM. But we need alpha TC. So alpha TC is equal to RTC divided by R day. So 30.75 divided by 50, we get 0.615. That one is the alpha TC, the coefficient, runoff coefficient. So since we have TC, cukup dah. QD is available. QD is from question 2. So Q runoff is equal to QD 14.7 times alpha TC is 0.615 times A is 1.5 divided by 3.6 divided by TC is 1.23. So peak runoff, peak runoff is 3.0685 meter cube per second. Alright, so I think that's all. Any question you can raise? Don't forget about the project in the tweaks. Then I give the Q.